Hello, time for a super important lesson. We're going to use this idea for the rest of the year, so pay attention. We're going to talk more about forces and discuss how to analyze all the forces on an object. But first, do this question. Great job on that question. Okay, so yesterday I showed you guys a video. There was like a big iron ball. It was 2 kilograms and was hanging from a string. Forget about that. Here I have a 2 kilogram rock. Imagine I put it on a table that you can't see. A table right there. Perfect. I don't know how to... We're just into it. This is called a free body diagram, also known as a force diagram. But for some reason, physicists like to say free body diagram or FBD. So the table with the rock might look like this. I'm not an artist, as you can tell. But you don't need to be an artist. To draw a free body diagram, step 1, make a dot. The dot represents the object, in this case the rock. Don't draw the rock, don't draw the table, just draw a dot. Simple as that. Then, think about every force on the object. A force is anything pushing or pulling on the object. And for every force on the rock, important, not from the rock, only on the rock. Only things that are pushing on the rock or pulling on the rock. You draw a force vector representing that force. So there's one force we talked about last lesson, gravity pulling down on the rock, Fg. If it's a 2 kilogram rock, I'm going to round, it's about 20 newtons. I got that from the formula Fg is m times g, which we talked about yesterday. What else is pushing or pulling on this rock? Well, the rock's not falling through the table, it's being pushed up by the table. So there's a force pushing up. Listen to the words. There's a force pushing up on the rock from the table. We don't draw the force from the rock on the table. For the rock's free body diagram, only draw the force on the rock from the table. I'm going to call it force Fn, which we'll talk about why soon. And if you can figure it out, I'm not going to. If you can figure it out. What's Fn? Well, we know the rock is at rest, stationary, not changing velocity, not accelerating. The rock is therefore in a state called equilibrium. So Fg is 20 newtons downward, Fn must be 20 newtons upward. The vector sum is not 40 newtons. 20 up plus 20 down is 0 newtons, equilibrium. Equilibrium means the net force or total force is 0. Net force means total force. You can write F net, not Fn. Fn is something different. F net, or you can do capital sigma F. These are 0. That's equilibrium. An important note, equilibrium does not mean not moving. Equilibrium means net force is 0. It could be moving. This is a hint for later. An object with no net force on it will keep moving if it was moving. If an object's moving and there's no net force, it'll just keep on moving right through space. Yeah. There's a lot of different things I want to talk about. So here's a quick free-body diagram. Let's say we have a plane that's going through, it's cruising. It's in the middle of a transatlantic flight. It's flying. It's a constant level speed, level altitude, constant velocity, not changing anything. What forces might there be? There might be a force of gravity pulling it down because it's heavy. There might be a lift force from the wings. You can just label forces whatever you want to label them, except for a few cases we'll get to really soon. There could be drag. We usually ignore air resistance and drag, but sometimes you don't. Sometimes it exists. So I'll call it FD for drag. And maybe the engines are kind of firing a little bit. Maybe there's some FT, some thrust. If it works out that these four vectors add up to 0, don't say they cancel. I know you can say they cancel. It's better to say they add up to 0. Definitely don't say they're equal. They add up to a 0 total force vector. Then it's in equilibrium. A plane can be in equilibrium. That's not a problem. All the examples we'll see today are in equilibrium, but these are two free body diagrams. This is a rock on a table. This is a plane flying through the sky. In both cases, the net force, total force, is 0. All forces are newtons. Let me talk about newtons really fast. Newtons are named after Isaac Newton, in case you guys were curious. I mean, they're probably weren't, but pretty obvious. He's really famous for this crazy story where he's chilling under a tree and an apple falls and hits him on the head. This is a nice reminder of what a newton is. A newton is the force. A newton is the unit of force. And we learned about one force already, weight. A newton is a pretty small force, a really small force. I weigh like 2,000 newtons. Is that right? I'm gonna go on a diet. But a nice reminder, something to help remember. Think of Newton, apple falling on his head. A small apple weighs about 1 newton. Nowadays we have like big GMO apples, but back in ye old days when there weren't any like fertilizers, pesticides, and stuff like that, apples were kind of small. A small apple weighs about a newton. Like a chicken egg probably weighs about a newton. So it's a very small force. So that's good for you to know. So we talked about Fg, the force of gravity. There's a lot of other forces we can talk about. There's friction, when things rub against each other and they're kind of rough, like rubber on like asphalt or whatever. Frictional force, we always make like a little curvy F. You could do FF, that looks kind of like silly. So a nice curvy, ooh, what a fancy F. That's frictional force there. Anytime you have a string or a rope or a cable or like a chain pulling on something, we call that a tension force. Ft is tension. That's very common. Fg, Ff, Ft. We don't really talk about drag force. We don't really talk about lift or thrust like in the plane. We talk about gravity, friction, tension, and the table. Remember, there's a table with a rock on it. There's a force called normal force. It's a very normal thing. Normal force is the force exerted on solid objects when they push on each other. So if I put a rock on a table or even on my hand, the force from my hand on the rock is a normal force. I'm pushing the rock up with normal force. It's not called normal force because it's a normal thing. It's called normal force because it's always perpendicular to the surface. Right now on the rock, the force is upward, because upward is perpendicular to the table surface. If I grade some labs and they're terrible, I get really mad, I punch the wall, bam. The force from the wall on my hand will be like this. You can't really see it, but it's normal or perpendicular to the wall. I don't know why people use the word normal for perpendicular. It's really confusing. You might have heard it in math class, but no one ever uses it anymore, except in this case. Normal force, when objects push on each other, there's a force perpendicular to their surfaces called normal force. These are the main forces we'll look at for this lesson. I can't think of any more. I think I talked about buoyant force later, but it's not really relevant to this class. So let me show you one more thing and then we'll end for today. Inclined plane, a ramp. So let's say I have a ramp, angle theta. Let's say I put a block on the ramp. And let's say it's a rough ramp and it's a pretty small angle, so it's in equilibrium. It's not sliding. It's stationary on the ramp. Well, first step of free body diagram, draw a dot. This is the block's free body diagram. Ignore the ramp. Only forces on the block. Second step, list all the forces on the block. Tell me all the forces on the block. Let's do it together. Hey babies, what's one force on the block? Gravity. Yes, gravity, good job. Gravity for problems on Earth is always straight downward. What's another force, babies? Normal force. Yeah, normal force, good job. If the surface of the ramp is like this, the normal force is not straight up. This is why I'm doing this example. For a table, yeah, normal force is straight up. But normal force is not always straight up. The normal force would be perpendicular to the surface. People always think normal force is opposite gravity and equal to gravity. Not necessarily true. In this case, not true. There's one more force. I said the ramp's really rough. It's not sliding. The block is in equilibrium. Friction. Yeah, good job. Wow, hey, friction. F. F. A nice fancy F for friction. Great. Oh wait, just kidding. It's not great. This is bad. We have to resolve these vectors into x and y. We can't solve for anything if we don't know x and y. In this problem, we know fg. Let me slow down. We can find fg in this problem. It's mg. It's always mg. Easy. But how do we find fn and ff? There's no formula for fn. There is a formula for ff, but we're not using that today. We have to find it, but it's really hard because they're both diagonal. We have to do a lot of vector resolution. We have to use, oh, this is theta, and this isn't theta. I happen to have taken geometry in my life. This is theta. This top, not this. This would be 90 minus theta. Okay, look at the picture. It's kind of annoying. We have to say, well, this is fnx, fny, ffx, ffy, and we have to set them all equal to 0 to get this. I have an amazing trick that's going to help us out. Normally, when you look at a problem, you'll say, okay, well, up is y, and right is x. That's how you would approach a problem. Watch this trick. It's going to be amazing. Take x and y and just go like this. Instead of x and y, these are my directions. You could call this y and this x, but they're not really y and x. It's not really clear. Since this one's parallel to the ramp, I'll call this parallel. And since this is perpendicular to the ramp, I'll call this perpendicular. You can do that. It's fine. It's not a problem. X and y are perfectly fine coordinate axes, but so are parallel and perpendicular. Except they both start with P, which is not ideal. But I use these symbols because that's because they look nice. Yeah, good job. Why is this better? Do you guys see why this is better than X and Y? Look at my free body diagram. FF is only parallel. FN is only perpendicular. If we want to resolve the vectors to set them equal and solve, instead of resolving two vectors, we can resolve only one vector. So we're going to resolve FF. Normally what we do, when we, like in the projectile problems, we'd have, we have a velocity v, and we say, here's Vx, here's Vy. This is vector resolution. We're not going to do that with X and Y. We're going to do it with this. This is FG parallel, and this is FG perpendicular. You guys see those? All right. See if you can use the picture and your knowledge of geometry to tell me what's FG parallel, what's FG perpendicular. What are the formulas? Formulae is technically the plural of formulas for FG parallel, FG perpendicular. Tell me the formulas. A lot of people will look at the picture and say, the angle in the bottom left is theta, so this is theta. It's not theta. This is theta. You can probably tell based on this picture, but I'll draw it up here. Even though you don't really draw it up here. I'm doing it today. This is FG. This is perpendicular. This is parallel. I messed up the drawing. That's where the block is. Here's FG. Here's the perpendicular component. Here's the parallel component. Why do I know this angle is theta and not this one down here? If this is theta, this is 90 minus theta because it's a right triangle. The three angles add up to 180. This is 90, so these two add up to 90. So this is theta, this is theta's complement, 90 minus theta. This angle right here also makes a 90-degree angle with this angle. So this is 90 minus theta, this angle right here is 90 minus the quantity 90 minus theta, which is theta. So a little trick, everyone always says, theta, bottom left, right there. No. If the incline makes an angle theta with horizontal, this angle up here is theta. So FG perpendicular will be mg cosine theta, and opposite will be mg sine theta. And then all the forces add up to 0. Now this is where we have a nice trick. X and Y are independent. Why did I say that? X and Y are independent. Oh, I remember. X and Y are independent. What are Fn and Ff? Tell me. What are Fn and Ff? How do we solve for Fn, the normal force, and Ff, the frictional force? It's not a formula. Look at the problem. We know it's equilibrium. We know that F net equals 0 newtons. But it's a vector. So we know that we could say F net x equals 0 newtons, and F net y equals 0 newtons. I'm writing a lot. But actually, we're going to say F net parallel is 0 newtons, and F net perpendicular is 0 newtons. So it's kind of messy. Look at this free body diagram. We resolved Fg into these two, so we can ignore Fg now. There's only two forces that are perpendicular, Fn and Fg perpendicular. So Fn is mg cosine theta. Sorry for the messiness. Hopefully your notes are a little nicer than this. We solve, look at Ff. I didn't draw it in the right place because I resolved the vector. But Ff is down the ramp, Ff is up the ramp. There's no other forces up the ramp or down the ramp. There's no other forces parallel to the ramp. So if Fg parallel is mg sine theta down the ramp, Ff must be exactly mg sine theta. So a nice little trick, where you see the inclined plane, resolve Fg like this. If you can't memorize it, you can derive it again. If you need a little trick, make sure it makes sense when theta is 0. If theta were 0, you wouldn't need any friction to keep it up the ramp. So Ff would be mg sine theta, which would be 0. Great. If it were flat, if theta was 0, then all the force of gravity, then the free body diagram, sorry for the terrible, would look like this. Sound effects very relevant. Fg and Fn would be equal. Well, would they be? Well, theta is 0, mg cosine theta would be mg. Fg would be equal to Fn. Perfect, it works out, good. Because cosine of 0 is 1. So it does work out if theta is 0, so that's going to check your reasoning if you forget this exact derivation. It is very messy, but the practice problems are going to be really important, and we're going to use this whole unit and probably the next like 5 units too. So really learn the method to draw free body diagrams.